Cedric. Today we're going to talk about chords and arcs. So more circle things. A chord is a segment whose endpoints are on a circle. So it doesn't necessarily have to go through the center. Okay, and you can see it there, P and Q would be a chord. And so it says that the diagram shows chord PQ and its related arc, which is also PQ. Make sure you note the notation, okay, on that whole thing. So the line PQ is the chord, and then if you have the arc over it, then that would be the arc of that. Here's theorem 12.4, which the 12.4 doesn't really matter, but here's the theorem and its converse. Remember, it can go in both directions. This says that within a circle or in congruent circles, congruent central angles have congruent arcs. So if angle AOB is the same as angle COD, then arc AB and arc CD have to be the same length. Okay,
How do we know AB?
It'll be given to you.
Okay.
Or it'll be something you can figure out. And then the converse of that is, if you know that you have congruent arcs, then their central angles have to be congruent. So it's just stating the same thing both directions. Okay, here's theorem 12.5 in the converse. It says that within a circle or in congruent circles, congruent central angles have congruent chords. Okay, so if you've got these central angles here are congruent, then the chord AB and the chord CD would also have to be congruent. So similar type of a thing, except for now instead of saying the arc, they're saying that the chords have got to be congruent. And then backwards, if you know that the chords are congruent, then you know that the central angles have to be congruent as well. And then give you the example on the right-hand side. Again, if AOB, angle AOB is congruent to COD, then chord AB and CD have to be congruent, or you can flip the if-thens. Okay. All right, 12.6, it says this. Within a circle or in congruent circles, it's just telling you could have it within one circle or two of the exact same circles. All right. Congruent chords have congruent arcs. So if B, chord AB is congruent to CD, then arc AB would also have to be congruent to arc CD. And then, of course, you can flip those. If you know that the arcs are congruent, then the chords would also have to be congruent. All right, theorem 12.7 says this. Within a circle or in congruent circles, chords that are equidistant from the center, you can see that here by these red lines that say they're the same distance, or centers are congruent. So you can see that there. So that means that because OE and OF are the same distance, then chord AB and CD have to be the same distance or same length. Or you can flip them around. If you know that AB and CD are congruent, then OE and OF have to also be congruent. All right, 12.8.
Yeah, so
In a circle, if a diameter is perpendicular to a chord, then it bisects the chord and its arc. Okay, so if the diameter goes to the chord at a right angle, then it's going to be a bisector, perpendicular bisector, splits it into two even parts. That's that first one, 12.8. So you can see that there from the picture on the right, which also means that it splits up the arc into two congruent parts as well. On 12.9 it says in a circle, if a diameter bisects a chord that is not a diameter, then it is perpendicular to the chord. You can see that there as well. Okay, in a circle, if a diameter bisects a chord that is not a diameter, then it is perpendicular. It's just saying the same thing but backwards. Okay, you guys see that? 12.8, 12.9. It's telling you if it bisects it, then it's going to be. All right, 12.10. In a circle, the perpendicular bisector of a chord contains the center of the circle. So all three of these are together on the same slide because they're pretty much all saying the same thing, but you were given different information to start with. All right, so in exercise 1 and 2 here, they tell you that the two circles are congruent. And you need to tell what we can conclude. There should be a lot of stuff that we can conclude. We'll name a few things. So we don't need to say stuff like PQ and AB are congruent because we can see that it's given in the thing. But what are some things that you can tell me about this that you know one thing at a time? Go ahead, Jordan.
the chords are congruent.
Which chords?
PQ and AB.
So PQ.
What?
Minor
Okay.
Wait, what's so funny?
I don't know.
We just said. No, we already just said. That's
exactly
what you
just said not to say,
What?
because it's given.
No. She said. Oh, did she say the chords? Did you say chords?
Yeah.
Oh, I'll pretend she said arc length then. So the arc length was if they gave us the chords were congruent.
Okay, whatever.
The second angle PXQ is the same as AEB.
It's congruent to what? AEB?
Yeah.
Okay, good. Who else? Go ahead.
Chords SR is congruent to DC.
SR and DC. Okay, yeah. And so then, because you know that SR is congruent to DC, it's because of vertical angles, right?
Right.
So then you also know that SXR, and we're not going to do all of these, okay? Because we could go on for a long time, is congruent to what? DEC?
Are they always doing vertical angles?
Not always.
And then
Sometimes
you have arc SR and arc DC.
You could say, well, couldn't you say that arcs,
PQ or PC and AB
And-
QR and DC.
right. So we could go on for a long time, but you guys are getting the gist of it. Okay, on 2, they give us that 2 arcs are congruent, so that tells us what?
Oh, W
WY and
DF are congruent.
DF are congruent.
WXY and DEF.
Say again.
WXY and DEF.
Angle WXY is congruent to angle DEF. And again, you guys get the gist of it. So you can go on and on with things that are congruent on these things. All right, so you get the idea of some things that you can conclude based on those rules that you've learned. We did not get them all, but we got a good number of them. Okay, next, we need to find the value of x for the given information. What's x? X equals 8 because of our rule that says that if it's equidistant from the center, then the chords have to be congruent, right? What about over here?
12.6.
Oh, yeah, she's right.
Help.
Everybody see it?
Yeah.
No.
If this is 6.3 here, then this also has to be 6.3, which would be 12.6. You guys don't think that this is 6.3. I can see where the picture would throw you off, but if it's 4.9 here and it has the same hash mark, then they have to be both 4.9. So 6.3 and 6.3 is 12.6, so x would equal 12.6. So a lot of this is just going to be those rules that you looked at. On this slide, same type of thing. What's the value of x to the nearest tenth?
Questions.
About that. If you think that 8 is just this side, then x would be 16. If you think that 8 is the whole thing, you know what? Maybe it is 16. I don't know. But I will make it more clear. I'll make it more clear on the tests and quizzes. Typically what I'll do is I'll have the number right here at the intersection if it's the whole entire line, and I'll put it by the dash marks if it's just the dash mark. So we'll see how that goes. Or maybe draw an arrow. Okay, here we need to figure out what x is. So we're going to have to do a little bit of work. Anybody have an idea? What kind of triangle is that at the top, or the x is?
Right.
It's a right triangle, right? Because if this is 90 degrees here, then this has to be 90 degrees. Does anybody know what the distance is on this part of the triangle on the right-hand side? This is 9. And if this whole thing is 14, it's a bisector, this would be 7. So what can we use to find x? The Pythagorean theorem. So you have 7 squared plus x squared equals 9 squared. 49 plus x squared equals 81. Subtract 49. X squared equals 32. Square root.
So are we allowed to assume that the point is in the middle of the circle?
Yeah, if they give you the dot, it'll be the middle of the circle. If they give you a dot, they won't put it if it's not. So this would equal the square root of 32, which is 4 square root of 2. And if somebody wants to type that in, we can get an approximation, but what's the square root of 32 equal to?
5.7.
Or about 5.7. Okay? The other side, they want us to find x, and they give us certain information. It looks like they're telling us that 10 is that entire line. Would you agree with that? Okay, so we need to figure out what x is. Does anybody have a clue as to how we would do that? Okay, go ahead.
Okay, so you kind of pretend like the line of x like keeps going, you know, and so then you do, or then you do like x. Well, then you would be like that right there would be like y, and then you do 5 squared plus 4.2 squared.
Hold on.
Equals like that y.
Yes. All right, look. All you have to do is draw this line from here to here, and that has to be x also because it's a radius.
Oh.
And so you have a right triangle. So So if this whole thing is 10,
Oh.
then this would be 5. And so you do 4.2 squared plus 5 squared equals x squared. So all we have to do is take the square root of this. So somebody type in the square root of 4.2 squared plus 5 squared. And what do you get? Square root of 4.2 squared plus 5 squared. What is it?
6.5.
Okay, x equals about 6.5. So we're still going to have to use some Pythagorean theorem stuff, but you guys can see how to draw the triangle. Don't get confused. Remember, if they want you to find a radius, that radius can go anywhere from the center to the outside of the circle. Okay, here they give you that circle J with the diameter HK. They tell you that KL, the arc KL, is congruent to the arc LM, right? KL and LM, so we'll say this arc, and then from here all the way around, I don't know how to mark that, like that, I guess, are congruent, and MK and LK, right? So all three of these are congruent, and they want you to prove that triangle KIL is congruent to triangle KIM. So we can probably write out some stuff. Do it as a paragraph proof and you'll be okay if you want. Or you don't have to. You can do it as a two-column proof. It doesn't matter. So what are some information about the triangle that you know? Kale, give me one thing.
I'm pretty sure you can say KM and KL is very
You could say KM is congruent to KL, which is also congruent to what? ML. Okay?
Because of what?
Because of whatever that theorem is, it says that congruent arcs have
So what
congruent.
would you say in a proof though?
Okay, so if you guys, you're not going to memorize the formulas, even though the book, if you ever look in the back of the book, it's going to say because of formula 12a or theorem 12a. You're not going to do that. What you can say is this. You want to do shorthand, congruent, chords have, I should have written it the other way, congruent arcs. It should have been congruent arcs have congruent chords, right? So it doesn't really matter. So that would be enough for me, that I would know that you knew the rule. Okay, so now we know that this, and this is all the same. Okay? Now what? Sarah?
Can we say, wait, can we have, what is the point where, between M and L? Is there a point at all?
I.
Because we could say that point.
It's I.
Okay, I. So MI and LI are congruent because the, KH is a perpendicular bisector with an L.
Okay. Okay, so we're going to have to note that too. So we should probably note that first. We should probably note that what KH is a perpendicular bisector of ML. Okay. Line KH is a perpendicular bisector.
How do we know that for sure?
We had a rule of what, ML?
Mm-hmm. Oh, the diameter chord.
Okay. Okay, when a diameter goes through a chord. Okay? It's one of your theorems. All right? So, and, well, it's perpendicular bisector anyway. So diameter bisects chord. Okay, shorthand. I'm just doing shorthand. That's all you guys have to do. We did a whole chapter on proofs, right? So as long as I understand, then you should be in good shape. So now you can say that MI is congruent to IL, perpendicular bisector, which you've already said above. So it's better to say the perpendicular bisector thing first, so you can say that. Okay, go ahead.
How do you actually prove the second one? Because it doesn't tell you that the diameter bisects the chord.
They just do.
That's a theorem.
That's one of the theorems.
I know, but like, you know, you have to like, if this, there's no if. Because like, if we don't have like. If
Well, we could
it's
split.
making-
We could separate the arcs. There's two congruent parts too, if we wanted to.
Split the arcs.
Okay, say you
Say,
did.
like on the proving side, diameter bisects chord, but it doesn't tell us up there that diameter bisects chord.
But we know that already.
Like we don't know that those two sides are congruent. That's like what I'm saying. We don't know that it's perpendicular.
Oh, I see what you're saying. So you're saying that.
We have no way to prove that that's true.
Well, okay, so You're trying. Oh, I see what you're saying. So you're trying to say that the diameter could go through, and it wouldn't be perpendicular. Except for the problem with that would be is that we have an equilateral triangle, so the only way it could hit that chord is if it bisects it.
But don't we have to like say that somehow?
Yeah, we could probably state that, but I think if you guys told me the diameter bisects the chord and you already showed that it's an equilateral triangle, it would be fine. I would assume that you already know that because of previous work. I shouldn't do that, but we've already done a lot of proofs, so I'd be okay with that. And in all honesty, you could have solved this problem without doing that anyway. Okay? Because still, what you could say is, you could say that angle KMI is the same as angle KLJ, isosceles triangle, right? So you could do that. There's a bunch of different ways we could solve it. You guys
You can
understand?
also say the right angles.
Yeah, we could do that in the middle. So KM what? I
Yeah.
is congruent to
KLI.
KLI. Okay, isosceles triangle.
So that KI equals KI.
KI equals KI. Remember what that's called? Do we have enough yet?
Yeah,
Yeah.
say side, side, side.
We could have said side, side, side without the angle, or we could say side, angle, side. Now we could say all kinds of
Angle,
stuff.
angle side, or is that a real thing?
There, angle, side, angle is one.
Angle, side, angle.
Yeah. Angle, angle, side, you would have angle, side, angle, because if you have two angles, you know the third. So we could say, right now, with everything that we've written down, we have multiple ways that we could say that these triangles are congruent. You could say side, 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 angle, side, all kinds of stuff. Okay, so this is the kind of proofs you're going to be doing. Okay, in this picture, they're telling you that circle N and circle O are both congruent. PQ is a chord of both circles. Okay, you can see that line. It says if NO equals 12, I'm going to go ahead and label stuff. If NO equals 12, so this whole thing is 12. I don't know what the best way of labeling this is. Okay. NO is 12 and PQ equals 8. Use a different color. That's 8. How long is the radius to the nearest tenth of an inch? Okay. And the radius of both circles are going to be the same. Does everybody agree with that? Because they're congruent circles, right? Okay. So we need to find the radius of the circle to the nearest inch. So they give you 8 and 12. What is your plan of attack? You guys want? So what we need to do is we need to make a right triangle. You can make it one of 4 different ways. It doesn't matter. It's all going to be the same triangle. Okay? I can either draw from N, a line from N to P, or O to P, or N to Q, or O to Q. And since Andrew said go from N to P, we'll do it that way. And so now you can label sides. What's the bottom of this? 6. What's the side going to be? 4. And so we need to use the Pythagorean theorem to find what the radius is.
So it's 36
Okay.
plus 16.
6 squared plus 4 squared equals, what do you want to call C? Equals C squared. So 36 plus 20, or plus 24, plus 16 equals C squared. 52 equals C squared. We need the square root. And you get what?
7.2.
Yes.
So we got the distance was C.
That's it. That's the radius. It's going from the center to the edge of the circle. So everybody, a lot of people get lost in all the lines in the middle. You just kind of have to piece together information you know. You know we've done a lot of right triangle stuff. And then you can also use some of the rules that we've had, that we learned today. All right, here's what we're going to work on today. 7 through 31 odd, don't do 29.